Okay, welcome everyone to Physics 390 Class 17. This class will be on solid lattices. And in this class, we'll look at several models of how electrons fill up energy states in solids, and how properties of solids are determined by that. Two particular models we'll look at which simplify the complicated way that electrons fill up energy states in solids are one, the free electron gas, and two, the block theory of a periodic potential. So we'll get into those in a second. And this comes from chapter 5.3 of our textbook. Okay, so let's get started. Valence electrons and two useful approximations. So in a solid lattice, there are inner electrons, which are bound to one nucleus. So the electrons which have lower energies in each, with regard to each nucleus, tend to stay bound to that nucleus. There are also valence electrons, which are more loosely bound. Those are the outer ones with the higher energies. And those in a solid, they tend to spread out and become delocalized, and the wave functions spread over a set of atoms, and they experience the lattice potential. So not just the potential of one atom, but the potential of a lattice with a grid of energy structures. So those are valence electrons. Those are the outermost, which experience the lattice potential. Okay, so electron-electron repulsion makes things complicated, as we saw for most atoms. In most atoms, with electron-electron repulsion, we can't solve analytically for the wave functions of the atoms. We have to make some approximations and ignore the electron-electron repulsion and then make corrections for it. So the same thing goes for solids. Electron-electron repulsion makes things complicated, but there are two approximations which can help shed light on the basic behaviors of solids. Okay, and as we mentioned, the first one is called the free electron gas approximation. It ignores all forces, so it ignores the attraction of the nuclei to the electrons, and it ignores the electron-electron interactions. What it doesn't ignore is the solid's edges. So the electrons here, the valence electrons, are treated as we call free fermions in a three-dimensional box. So these little circles here would be the fermions. This is the box, which is the solid dimensions, and they're trapped within that box. Okay, so we'll analyze how that works in a second, but just a sort of the upshot of it is it demonstrates how the Pauli exclusion principle is very key to the stability of solids. And we'll see how that comes out in our analysis of it in a second. But it predicts, the free electron gas approximation actually predicts that all solids should be conductors, which is clearly not the case. Most metals are conductors, but other materials like plastic or rubber or glass or wood are not conductors. So the free electron gas approximation has its limitations, but it does show that it does have a good explanation of the stability of solids. The second approximation we're going to look at is called the block theory approximation. It ignores all forces except the solid's edges again, and it ignores electron-electron interactions, but it does have the electrons interact with a periodic 3D lattice potential of electrical origin. So the valence electrons interact with that. And this is sort of a schematic of that. You can see that this is a grid of atoms with a potential energy which varies periodically as you move throughout the grid of atoms. And these little dots would be electrons, valence electrons interacting with that and having energy levels determined by that grid. So Note that this is a 2D lattice potential pictured here. This is a two-dimensional with the height being the value of the periodic potential. The 3D would be very hard to display because it would be there'd be a a value at each point in space, which we'd have to show. So this gives the flavor of it anyway. And the block theory approximation actually can account, whereas the free electron gas approximation predicts that all solids should be conductors, the block theory approximation can account in broad terms for the distinction between conductors, insulators, and semiconductors. It doesn't get everything perfectly right, but it can give in broad strokes, a way to think about why some solids are conductors, some are insulators, and some are semiconductors. Okay, so let's look at the free electron gas approximation. So here's our little picture of it with the free electrons in the little box. So we start with a 3D box, and we solve the TISE for a 3D box. So it has length, the box has dimensions Lx, Ly, and Lz, so three potentially different dimensions. So we start with the TISE, we separate variables into X, Y, and Z. And what we find is that it separates into three one-dimensional infinite square wells. So the stationary states would be labeled by Nx, Ny, and Z. And one-dimensional square well has a coefficient square root of 2 over L, or Lx in this case. So when we have 3, we'll have 3 of those factors: square root of 2 over Lx, square root of 2 over Ly, square root of 2 over Lz. So we get square root of 8 over Lx, Ly, Lz. And then the familiar sine functions for each individual infinite square well in the X, Y, and Z directions, with allowed values of the coefficients here. And the energies of Nx and Y and Z are just the sum of the energies of the infinite square wells in each direction. So here's the Nx squared over Lx squared times this constant L in front, the Ny squared over Ly squared here, plus the Nz squared over Lz squared here. And that can be written, since pi squared Nx squared over Lx squared is Kx squared, because Kx is Nx pi over Lx. It can be written as h bar squared over 2m Kx squared plus Ky squared plus Kz squared. Or just, if we take this K squared to be the sum of these three, it would just be h bar squared K squared over 2m. Okay, so each of Kx, Ky, and Kz have this relationship, Nx pi over Lx, Ny pi over Ly, Nz pi over Lz. Okay, so those are the stationary states we have and the energies. So how do the electrons fill up these energy states? Well, to do that, we imagine the space of Kx, Ky, Kz to be divided up into state blocks. Okay, so state blocks is a unit of the Kx, Ky, Kz space, which contains one energy state. And each of them would have volume of, so since Kx is starts at pi over Lx, and the next value would be 2 pi over Lx, the width of that first state block would be 2 pi over Lx minus pi over Lx, or pi over Lx. Similarly for y, it would be, the width of it in the y direction would be pi over Ly. The width in the z direction would be pi over Lz. So the volume of these little state blocks, which is kind of pictured here, so this is Kx, Ky, Kz, and these lines occur at multiples of pi over Lx in this direction, pi over Ly in this direction, and pi over Lz in this direction, all potentially different, not necessarily square, because Lx, Ly, and Lz could be different. But this shaded rectangle, or shaded rectangular prism here, is the volume of a state block in this kx, ky, kz space. And it would be pi over lx times pi over ly times pi over lz, or pi cubed over lx, ly, lz. And notice that since we said that our dimensions of our object are lx, ly, and lz, this would be the v, which is the volume of the object. So each state block has a volume pi cubed over v. Okay. All right. So we know what the volume of each little state in kx, ky, kz space, or k space is. So how do the atoms fill those up? Well, they're fermions, so they're not gonna all fill up the one of the states. They only one of them, well, only actually two electrons, because of the spin of the electrons, can occupy each state. So we have n atoms suppose we have n atoms in our solid of volume V. Each of them has d valence electrons. That gives n times d total electrons, free electrons. And those will fill up the state blocks in spin singlet pairs. So an antisymmetric spin state to make the wave function antisymmetric, because this is a symmetric combination of space states. So, so they'll fill out these state blocks because there's only, they're fermions, so only two of them can fill out the one state block. So they'll fill them up out to a maximum radius in K. So K will be getting greater and greater. And as a result, the energy will be getting greater and greater. And how do we determine that maximum K radius that the electrons will fill up to? Well, we can kind of look at this picture here. This is Kx, Ky, Kz. Kx, Ky, Kz are positive. So the states would all be in this first octant of the three-dimensional Kx, Ky, Kz space. And as we move out and K increases, the energy increases. And so we fill up states in this shaded volume here. And we can measure that shaded volume in two ways. We can just write that where Kf is the maximum K radius. So Kf would be this maximum K radius that is filled up. The volume of that would be the 4/3 pi Kf cubed. That would be the volume of a sphere, but we're only looking at 1/8 of the sphere, one octant. So the volume of that would be 1/8, the 4/3 pi Kf cubed. Okay, that's also equal to the number of spin singlet pairs, which would be nd over 2, since there's nd total electrons, divided by 2, since that's the number of pairs, times the volume of each state block. So, so those two would be the total number of electrons pairs times the volume in this space of each state block must be equal to the calculated volume out to the maximum K radius. Okay, so we get this relationship here. We can solve this. Let's see. So let's see. 4/8 is 2. Well, we have 2 in the denominator. That cancels this 2. We cancel a pi, so we have pi squared over here. We bring up a 3, so we have 3 nd over v pi squared is Kf cubed. So Kf would be 3 nd pi squared over v to the 1/3 power. And we usually call nd over v rho, the free electron density. And if you look at that, that would be the total number of free electrons, nd per volume. So that's the free electron density, the volume density of free electrons. Okay, so we have this relationship for the maximum value of K that will be filled up given a certain free electron density, rho, and it's proportional to rho to the 1/3. Okay, well, we know that K is related to the energy, right? Because energy is proportional to K squared. So the energy at this maximum radius kf in k space is called the Fermi energy. And that's actually why we use the subscript F, because Enrico Fermi, the physicist, did a lot of work on this type of system. So it's named Fermi in his honor. The Fermi energy would be h bar squared over 2m times kf squared from this expression here. So it'd be h bar squared over 2m times this squared, or 3 rho pi squared to the 2/3. So this is the Fermi energy, proportional to the free energy density to the 2/3, free electron density to 2/3. The total energy of all electron states can be shown, and we see the text for this, to be equal to this expression. E total is equal to h bar squared times this expression involving the number of atoms to the 5/3 over the volume to the 2/3. Okay, so we're not going to worry about the detailed nature of this. You can see the text if you'd like to look at it. But we're going to note one thing about it. And by the way, this E total would come from integrating from k equals 0 out to kf, the energy at the different k values. So it's an integral over this space, which gives this result if you look at the text. So what we're interested in is if we expand the box that are solid by dV, if we try to expand it a bit, that's going to actually decrease the total energy. Because if we take the derivative of this with respect to V, we get minus 2/3 V to the minus 5/3. So we get minus 2/3 times all this times V to the minus 5/3 dV is dE total. There's a minus sign here though. So that can be rewritten minus 2/3 E total, which is all this to the times V to the minus 2/3 over V to make this V to the minus 5/3. So we get this expression here. dE total is minus 2/3 E total dV over V. Well, that may remind us of something. A change in energy being proportional to dV. What it's proportional to is actually minus the pressure. In thermodynamics, we have the change in energy being minus P dV. Okay, so we have a pressure here, an effective pressure minus P is minus 2/3 E total over V. So P would be 2/3 E total over V. So the box exerts an effective pressure, P equals 2/3 E total over V on its surroundings. Okay, that's even though we haven't talked about temperature or vibration of atoms or electrical interactions or anything. All we've talked about is the fact that the electrons are filling up states according to the fermion, the Pauli exclusion principle. Okay, so we can write this 2/3 E total over V in several forms here, which you can look at the textbook to verify these forms if you like. But this second form says that the pressure is proportional to rho to the 5/3. Okay, so it's proportion. It increases as the number of electron density increases, which makes sense. The more electrons we try to pack in, the higher the energy, and therefore the higher the pressure on the surroundings. So notice though that there's no temperature here. There's no T here. So this only depends on the density, free electron density, ND over V. It doesn't refer to whether the solid is hot or cold. So even though a hotter object will generally, because of the vibrations, which we have not accounted for in this model, because of the vibrations, it will exert more pressure. There is an independent pressure here due to the Pauli exclusion principle and the electrons filling up these states, which is represented by this pressure here. So even a very cold solid object exerts this quantum pressure. So even if we cool something down to very low temperature, it's going to exert this quantum pressure on its surroundings. So if we take a solid and make it very cold, it doesn't vibrate very much, and there's not much thermal energy in it. So you might think if we put a weight on it, it would collapse. But because of this so-called quantum pressure coming from the Pauli exclusion principle, the solid remains stable and it won't collapse. So the free electron gas can explain why solids are stable, the stability of solids, and why they don't collapse even at low temperature. What it doesn't explain is the conductivity. Why some are conductors, some are insulators, and some are semiconductors, because there's a continuous range of energy states here, out to what we call the Fermi energy. So because of that, it can be shown that all solids the free electron gas is a conducting model of a solid. So all solids would conduct if they're modeled as a free electron gas. Okay, so that's the free electron gas. So let's look at another approximation, the block theory approximation, and something called band structure. And here's our little cartoon of the periodic potential that goes with the block theory approximation. So, okay, so a real solid has quite a complex three-dimensional periodic potential. If we look at a given atom or given element or compound, there'll be lots of atoms, lots of electrons around. So it'll be a very complex electrical voltage landscape. But we'll look at something simpler just to get the feel and the basic result. We'll look at a one-dimensional periodic potential, which is called the Dirac comb. It's called the Dirac comb because it has Dirac delta functions in it. And it looks like this. It's a strength alpha, and then a sum of Dirac delta functions at multiples of A. So we see here at 0, we have a delta function. At A, we have a delta function. At 2A, 3A, 4A, we have delta functions. And it kind of looks like a comb, the teeth of a comb, which is why it's called the Dirac comb. Okay, so to make progress on this, we use something for periodic potentials, a really powerful theorem by Felix Bloch, which says that for a periodic potential where V of x plus A equal V of x, and you can see that's true here, because if we shift over by A, we get the same, we're looking at the same potential. So it's periodic with period A. If that's true, solutions to the TISE satisfy the following. Psi of x plus A is e to the I QA psi of x, with Q a real number. Okay, so Q is just some real number. So as we move forward by A, we get the same wave function just multiplied by a phase factor, e to the IQA. And because of that, if we look at the modulus squared of psi x plus A squared, psi x plus A, that's going to be, let's see, e to the minus Q, e to the minus IQA psi star x, e to the IQA psi x, which is just the e to the minus IQA and e to the IQA cancel. And so we get just psi star psi, or psi x squared. So as we shift over, this is the probability density, remember, psi squared is the probability density. So as we shift over by A, the probability density shifts, the probability density stays the same as we shift over by A. So the probability density is periodic with period A, which makes sense because the solid it has the same potential as we shift over by A. So the local environment looks the same if we shift over by A. So we expect the probability density of electrons there to be the same if we shift over by A, even though the wave function is not quite the same because it's shifted by this periodic, by this phase factor, e to the IQA. Okay, so how do we handle the fact that the solid is not infinite? So we use what we call the wrapping, or sometimes called periodic boundary condition. Psi of x plus NA, where n is the number of cells, the number of, in the one-dimensional case, the number of atoms or unit cells in the solid, x plus n times a would be equal to psi x. So if we go, we make sure that as we go around the solid, at the end, the wave function has the same value. So this is a wrapping boundary condition, because when we go all the way around the solid, all the way to the other side of the solid, it's as if we've wrapped back around to the beginning, since it has the same value. Okay, this helps us because if, according to Bloch's theorem, if psi x plus NA is equal to psi x, then looking at this, that would mean psi x plus NA is e to the I n e to the I NA, sorry, e to the I NQA times psi x. So that means that, and that's supposed to be equal to psi x. So that means e to the I n big N QA would have to be equal to 1 in order for this to be satisfied. If we plug this psi x plus NA into Bloch's theorem, we get e to the I QNA psi x. So e to the I QNA must be 1. But that can only happen if NQA is a multiple of 2 pi, because e to the I is only 1, e to the I something is only 1 if that something is a multiple of 2 pi. So we have big NQA is equal to 2 pi times n, where n is an integer. We're solving for q, dividing by big NA, we get q is 2 pi little n over big NA, where n is an integer, 0, 1, plus minus 1, plus minus 2, etc. Okay, so this wrapping boundary condition gives us particular values of q, which are all real numbers, as we said it needed to be real, for which this which would apply to this solid. So there's allowed values of q for this solid, according to this. In general, n will be very large because atoms are quite small and most objects we look at are quite big. So n would be very large. So there would be quite a lot of these values q that would be allowed. N would really go from 0 up to a magnitude of capital N, but that would be a large magnitude generally, and capital N would be large. Okay, so the neat thing about Bloch's theorem is that we can just solve it over one of these little cells here, say from between 0 and a, and then Bloch's theorem determines the wave function elsewhere through this. So if we know psi x, where x is between 0 and a, then psi between a and 2a we could find from just plugging in this. It would be just e to the I QA times psi x. And then if we wanted psi between 2a and 3a, we would just add 2a here. So it'd be e to the I Q2a times what we get in between 0 and a. So through this relationship, if we know psi x for one of these cells, say from 0 to a, we can get psi a for the rest, psi x for the rest of them. Okay, so we just need to solve between 0 and a because of Bloch's theorem. So between 0 and a, we're not at the delta function. The delta function occurs right at 0 and right at a, at that particular infinitesimal point. So we can take v equals 0 in this range, solve the Schrodinger equation. We use continuity of psi, and as we saw in the solving the delta function for before, the delta function there's a discontinuity of d psi dx at x equals 0, where the delta function is. Okay, we won't go through all that math again, but you can refer to the textbook to see that. Even though this is not a well, but it's a spike, a positive spike, it still causes a discontinuity. So taking these continuity of psi at this position here, and the no discontinuity of psi at that position there, and simplifying yields this expression after a couple of steps. Cosine of QA, where Q is this periodic oscillation of the wave function, the coefficient of that, is equal to cosine of Ka plus m alpha over h bar squared K sine of Ka. And as usual, for the when v equals 0, K is related to the energy by K is square root of 2m e over h bar. So the energy is related to K. Alpha is the strength of the delta functions here, which tend to localize the electrons around a particular point. And Q is this periodic block factor. Okay, so what does this tell us? What physical insight can we get from this? So first we'll rewrite this just in a little bit more compact form. We'll take Z equal to Ka and beta equal to m alpha A over h bar squared. So then we get, rewriting this, we get cosine of QA would be cosine of Z plus beta over Z, because beta over Z would be this constant out in front here, because beta over Z would be m alpha A over h bar squared Ka, or m alpha over h bar squared K. So beta over Z gives us this coefficient here times sine of Z, sine of Ka. Okay. So just remember that Z is related to K and K is related to the energy. Okay, so here's where we start to get some insight, physical insight. The left-hand side must be between plus and minus 1, because the cosine function has to be between plus and minus 1. Meanwhile, the right-hand side has a cosine, which can be between plus and minus 1, but it also has this other term, which can put the right-hand side outside of the range from plus or minus 1. And if the right-hand side is outside of the range from plus or minus 1, the left-hand side cannot match it, because it has to be between plus or minus 1. So for those where the right-hand side is outside this range, this equation has no solution, and there will be no z values where this works, therefore no K, therefore no energies where that works. So let's see what that looks like. This graph shows Z on the, that is Ka, which is related to the energy, but Z on this axis, and the right-hand side here on the vertical axis. That's this wavy line here. Okay, so you can see as Z changes, sometimes this right-hand side is between minus 1 and 1. Sometimes it's not. Sometimes it's below minus 1. Sometimes it's above plus 1. It oscillates back and forth. Okay, so when it's between 1 and minus 1, then the left-hand side, we can find a Q value, an allowed Q value, which will cause it to match. And so we get this condition satisfied, and we get a stationary state of the potential there. So where the right-hand side is between 1 and minus 1, we get a solution. And those are called bands. As you can see here, this dark label, this dark shaded area is called a band. The places where the right-hand side is less than minus 1 or greater than 1, here in this case it's less than minus 1. In this case it would be greater than plus 1. We call a gap, because there's no way this equation can be satisfied, and there's no energies in this particular range of Z, therefore range of K, therefore range of E. So we have alternating gaps and bands, and in Z, which is alternate, means it's alternating K, which means it's alternating in the energy, which is related to K. So we can draw this diagram here, which has energy going on the vertical axis. This is an E. And we have this kind of takes this horizontal structure and puts it vertically, where energies are usually drawn vertically. So we would have initially a gap, and then a band, and then a gap, and then a band, and then a gap, and then a band, etc. So we have, this is called band structure. So where there's white here, where there's gaps, there's no electron energy levels there. Electrons simply cannot have those energies. Where it's shaded, electrons can have those energies. So okay, so what does that mean in terms of the behavior of solids and conductivity? Okay, so a conductor, we fill up these energy states, the available energy states, in the electrons fill them up one by one. Well, actually, each energy state gets 2 electrons because of spin, but we fill them up to the number of states here. How many electrons we have? We're going to have a topmost electron that is the highest energy state. The electron that is the highest energy state that gets filled. So in a conductor, the topmost band that is only partly filled. So electrons would be, say, filled up to halfway up this band. So right near the topmost electron energy, there is other available states. So there's room to excite those electrons by applying, say, a voltage or an electric field to the solid to stimulate those electrons up in energy and to get conduction going. Okay, so because it's the topmost band is only partly filled, that's a conductor. So that would be partly filled. In an insulator, the topmost band is filled. So the topmost electron, the highest energy electron, would be right at this boundary between the band and gap. So because of that, if we put an electric field on, or say raise the temperature to get more energy, it's going to take lots and lots of energy to get from the highest electron state to the next band, because there's this gap where there are no energies for the electrons to have. So in general, unless we really put on a humongous voltage or electric field, which would break down the material, we're not going to get any conduction. We're not going to get any electrons moving into higher states. So that would be an insulator. A semiconductor, so if we look up here, the topmost band is filled just like an insulator, but there's a very small gap above it, okay? So there's a very small gap. So the gap is not as large as this. So that means that sometimes, especially if there's sufficient temperature, so if it's not a really cold semiconductor, that there's energy around to boost those electrons, especially if there's an electric field around to stimulate them further, or of applied voltage, and we can get conduction across this gap. So it's semiconductor. It's called semi because it's kind of kind of a conductor. It's a conductor under certain circumstances, when it's not too cold, and when we have enough voltage to get the electrons across this gap. Okay, so we can through this band structure, this alternating gap, band and gap structure, we can understand what a conductor is, what an insulator is, what a semiconductor is. Conductor, partially filled topmost band. Insulator, topmost band fully filled and a large gap above it. semiconductor, topmost band filled, but a small gap above it. Okay, so and to sort of wrap up, we've looked at the behaviors of solid lattices. We've seen that in general, it's a very complicated problem because we have electron-electron interaction, lots of electrons around, and also interactions of the electron with the periodic lattice of the solid. We looked at two approximations, the free electron gas, which ignores both the lattice and the electron-electron interactions, just takes the electrons in a box. And it's able to, it doesn't explain conductors and insulators and semiconductors, but it does explain why solids remain stable at low temperature because of the Pauli exclusion principle applied to the electrons, filling up the states in the free electron gas. And then as our second approximation, we looked at the block theory approximation, where we take a periodic potential. In a real situation, we'd use a computer and use a 3D periodic potential, and it would be more computationally intensive. But we looked at a one-dimensional potential just to get the flavor of it. And we saw that even in that one-dimensional potential, because of the way the Bloch's theorem interacts with the boundary conditions at the boundaries between these cells, we saw that there's certain energies where there are stationary states and certain energies where there are not. So bands and gaps. And we could talk about conductors, insulators, and semiconductors in terms of those bands and gaps. Okay, so I hope this helps you appreciate the richness of the subject of conductivity and gives you a kind of a feeling for how a couple of, fairly conceptually simple models of a closed box and a periodic potential can give us insight into how electrons behave in solids. All right, thank you so much, and I'll see you in class.